In this video, I want to continue introducing you to sets, and I want primarily to talk about subsets. A set is considered a subset of another set if every element of the subset is also an element of the other set. So we look back at the first video where we talked about the universal set of all students at the University of Iowa, and set E being all elementary ed majors at the University of Iowa. Set E would be a subset of the universal set U, because everyone who's an elementary ed major at U of Iowa is clearly a student there as well. Here's another example using just some numbers. Set A, the numbers 10, 11, 12. Set B, the numbers 9, 10, 11, 12, and 13. We say that A is a subset of B because every element in A is also found in B. We see the 10 in A, there's a 10 in B. 11 in A, there's an 11 in B. 12 in A, there's a 12 in B. So we say that A is a subset of B. This is the subset symbol. I always think it looks like you've taken a paperclip and cut it in half. You can also think of it as sort of a squished down C with a line underneath it. Now the opposite here isn't true, right? B is not a subset of A. B is not, that's what that line means, a subset of A, because B has a 9 in it, and a 9 isn't found in A. So we know just by looking at that, B can't be a subset of A. If there's any element in B that's not in A, we know it's not a subset. We don't have to keep looking for 13. Doesn't matter that 13 is not in there either. As long as there's one element that's in B that isn't in A, that means B is not a subset of A. Equal sets are subsets of each other. So if set R is 1, 2, 3, and set S is 1, 1, 2, 3, 3, 3, R is a subset of S because every element in R is also in S. Remember, we only count elements once. It doesn't matter how many times they appear in our list. And the opposite here is also true. Every element in S is also in R. So equal sets are always subsets of each other. That's one way, in fact, that mathematicians actually define what equality means. The empty set is a subset of all other sets. So if set Z is A, B, C, D, E, the element, not an element, the empty set, the null set, is a subset of Z. Now, a little bit more confusing are proper subsets. A proper subset means that the sets are specifically not equal. There is at least one element in sort of the parent set, the set that you're comparing to, that is not in the subset. So the symbol for a proper subset is just that squished down C without a line under it. And that horizontal line means basically or is equal to, just like it does in a symbol like less than or equal to, or greater than or equal to. So for example, if set A is 10, 11, 12, and set B is 9 through 13, A is a proper subset of B, because there's at least one element in B that is not also in A. So the sets aren't equal. So all proper subsets are also regular subsets, but some regular subsets aren't proper subsets. So for example, neither of these are proper subsets because these are equal. They have the same elements in them. So they're subsets, but they aren't proper subsets. You can determine really easily how many subsets a set has by using this formula. First, you want to find the cardinality of the set, and that should read, call that cardinality N. The number of subsets will always be 2 raised to whatever the cardinality is. So if the cardinality is 7, it would be 2 to the 7th power. If the cardinality is 2, it would be 2 squared. If the cardinality is 37, it would be 2 to the 37th power. The number of proper subsets will always be 1 less than that. So it will always be 2 to the n, where n is the cardinality of the set, minus 1. For example, Let's say that we have set G, which consists of 3 elements: cat, dog, and fish. How many subsets does G have? First, we want to find what the cardinality of G is. G has cardinality of 3. There are 3 unique elements. So that means G has 2 to the 3rd power of subsets, or 8 subsets. If you don't remember how to find exponents, not an issue. Just use your calculator. Your calculator's exponent key. An exponent, really quickly, is repeated multiplication. So 2 to the 3rd power means you are multiplying not 2 times 3, you're multiplying 2 by itself 3 times. 1, 2, 3. And 2 times 2 times 2 is 8. 2 times 2 is 4. 4 times 2 is 8. It has 2 to the 3rd power minus 1. That would be 8 minus 1, 7 proper subsets. So let's add this to like a word problem. A student in your class announces really excited that his parents have told him that he could have any pet he wants. And he can choose a cat, a dog, or a fish. And he can choose any of them or none of them. How many different ways, how many different pets could he have when he makes his decision? We can list this out, which is easy with a few elements like this. Like making a list is super easy. If there were 10 elements in this, making a list would be much harder. But let's make a list for this one. So these are the subsets of G. So one possibility is the original. Cat, dog, fish. A student says, you know what? I want all 3. Maybe the student tells their parent, I want a cat and a dog. Maybe they want a cat and a fish. Maybe they want a dog and a fish. Maybe they want just a cat, or just a dog, or just a fish, or maybe they want no pet at all. These are the 8 subsets of set G. Notice that cat, dog, fish is the same as G. It's equal to G because every set is also a subset of itself. So we could write that G is a subset of G. Every set is a subset of itself. This doesn't count as a proper subset because that would be equal to itself. So G has 8 subsets. That's 1, 2, 3, 4, 5, 6, 7, 8. Or if we're ignoring the original, it has 8 minus 1, 7 proper subsets. One confusing part about subsets that people often struggle with a little bit is they get subsets and elements mixed up. That is entirely understandable. Your book talks about it a little bit, and understanding it just comes a little bit with practice. The final thing I want to talk about in this video is not directly related to subsets, but your textbook for this class talks about it in this chapter. And that's the fundamental counting principle, which is sometimes called the fundamental multiplication principle. And basically it's this. When you have a series of choices to make, the total number of possible choices is found by multiplying the number of choices you have at each stage. So if you are driving to school and you have more than one way to go there. So like, let's say, for example, let's use me as an example. I live in Bemidji, Minnesota. And let's say I want to drive from Bemidji to Minneapolis. And along the way, there's more than one way to get from Bemidji to Minneapolis. But I'm going to narrow it down a little bit. Let's say that to get from Bemidji to St. Cloud, I have 4 different routes. And then to get from St. Cloud to Minneapolis, I have 3 different routes. How many different ways could I go from Bemidji to Minneapolis? I have a total of 4 times 3. That would be, I have 12 different routes I could take to get from Bemidji to Minneapolis if I'm going through St. Cloud. If I had a more complicated problem and I was like, oh, I want to take a trip throughout the western US. I'm going to start in Minnesota and I want to go somewhere in North Dakota. And there are, let's say there's 3 different places I want to go in North Dakota, we'll say. 3 different ways to get to North Dakota. And then from North Dakota, I'm going to go to Montana. And to get from North Dakota to Montana, there's 2 different ways I can go there. And then from Montana, I want to go to Idaho. And there are 5 different ways to get from Montana to Idaho. And then I'm going to go back home, and from Idaho to Minnesota, there's like 2 really quick ways to go, and so I'm going to choose one of those 2 ways. These are made up examples, by the way. How many different ways could I take my trip? So I could take my trip 3 ways from Minnesota to North Dakota, 2 ways from North Dakota to Montana, 5 ways from Montana to Idaho, and then 2 ways back to Minnesota. That would be 3 times 2 is 6, 6 times 5 is 30, 30 times 2 is 60. There are 60 ways I could take my trip. These actually multiply really quickly. This is one reason why sometimes you'll go on the same route more than once, and your GPS might give you different directions each time, especially if it's a more rural route. At least that's been my experience. That's a little bit related to this idea. Like there are a ton of different possibilities to get from point A to point B in the real world. Let's look at some other examples. You're going to dinner at a restaurant. They have a special where from the selections they give you, you can get an appetizer, a main course, a drink, and dessert for $20. The restaurant has 4 app choices, 3 main course choices, 10 drink choices, and 2 dessert choices. How many unique meals could you get? So I want you to stop and think about this, pause the video, think about how many different meals, how many unique meals could I have at this restaurant? So using the fundamental accounting principle, I just multiply these numbers together. 4 times 3 times 10 times 2. 4 times 3 is 12. 12 times 10 is 120. 120 times 2 is 240. There are 240 unique meals. Now for all these problems, you could also draw what's called a tree. And a tree diagram is something you would do in elementary school with simple problems. It is hard to do with more complicated problems, right? There would be 240 end branches on our tree, which is, need a lot of paper for that. Really easy to miss something. But I'm going to give you a simpler tree example to conclude with. So you're getting dressed for work. You have 2 pairs of pants you can choose from, 2 pairs of shoes you can choose from, and you have 3 shirts to choose from. How many work outfits could you have? So fundamental accounting principle, really quickly, 2 times 2 times 3, I have 12 different choices. Here's what a tree of this would look like. So I have calling my first pair of pants P1, my second P2. So for my first pair of pants, I can choose shoe 1 or shoe 2. And then for each of these shoes, I have 3 shirt choices, which I'm just calling S. So one outfit would be pants 1, shoe 1, shirt 1. Pants 1, shoe 1, shirt 2. Pants 1, shoe 1, shirt 3. And then I keep going. And so in a tree, what I do is after I draw my tree, I count the final branches. And here I have 3, 6, 9, 12 final branches. I lied to you. I said this was the last thing. There's actually one more thing I wanted to mention that is brought up in this chapter, and that's called one-to-one correspondence. This actually goes with the last video. Any sets that are equivalent, that have the same cardinality, can be placed into one-to-one correspondence. And one way to show this is by drawing arrows. And your book talks about this as well. And I didn't draw my arrows right, but we're going to do it anyway. Let me add my other. So let's give this example. I have set A, which consists of the elements, the letters lowercase a through F. And I have set B, which consists of the elements you see there, 7, 9, 11, a bunch of 13s, 20, and 22. Again, it doesn't matter if an element's repeated. We only count it once. And so I've put arrows here just randomly, but it doesn't matter as long as for every element in set A, it could connect to exactly one element in set B. That means it's in one-to-one correspondence. All equivalent sets and all equal sets can be placed into one-to-one correspondence. So in this video, we talked about subsets and proper subsets. Some things to remember: every set is a subset of itself. The empty set is a subset of all sets. And you can find the number of subsets of a set by taking the number 2 and raising it to the power of the number of elements in the set. So if the set has 10 elements, it would have 2 to the 10th power. That would be 2 multiplied by itself 10 times, which is 1024 subsets. I hope this helps get some of the main ideas in this chapter, make them a little bit easier for you. In the next video for this section, I'm going to go over some of the practice homework for the chapter. Not the homework you're going to turn in, but the practice ones, to hopefully explain those to help you do well on the assigned homework. If you have questions about this video, please send me an email, and good luck as you move forward.